So in this video, we'll be discussing perturbation theory, right? And preferably, if you look at the board, we'll be talking about non-degenerate perturbation theory. Now, first of all, what we want is we want to understand what perturbation means. See, this perturbation has a clear link with the topics ahead, like it has a link with quasi-classical case. It has a link with scattering phenomenon that occur. Now, if I start with an example, come on. Suppose you have an ideal person, and this person is walking on a road. Okay, he's perfectly balanced. He's walking in a balanced manner, right? Now, somehow there is a small stone while he's walking on the road, and this stone he hits this stone, so momentarily the person doesn't feel a lot of change, but there is some kind of imbalance that's induced in this person's walk. So there is change in his original balanced state in which he is walking. So you can see that this small change, what was the small change here? The small change was this small piece of stone that came under his feet while he was walking on the road, right? So this caused the disturbance to his balanced walking, the way he was walking on the road. Clear? So I can assign this example with perturbation. So this person was perturbed. So now the question arises why I say a small stone, why I'm talking about the small thing, why I'm talking about a small disturbance. Because perturbation has everything to do with the small. And whatever you have calculated in quantum mechanics 1, you have treated ideal systems. You have solved Schrodinger's wave equation on these ideal systems. Am I right? So you have solved Schrodinger's wave equation, you know energy eigenvalues, and you know eigenvectors for those ideal systems. Now what we do when we subject this problem with some kind of perturbation. Now perturbation means a small disturbance. What we do here is we exploit the original unperturbed Hamiltonian. So what we have unperturbed Hamiltonian. And so if I have unperturbed Hamiltonian like this, we know everything about it. We know the energy eigenvalues. We know the eigenvectors of this problem, right? But what we are doing, we are subjecting our system to some kind of perturbation. Now this perturbation can be classified broadly into two categories. One is time-independent perturbation theory. The other is time-dependent perturbation theory. Now, in time-independent perturbation theory, we will have two classifications. The first one will be, we will have non-degenerate time-independent perturbation. And then we will have degenerate time-independent perturbation. Now the question arises, what is non-degenerate time-independent perturbation? So you should write down a couple of lines for this. So for each eigenvector, there is a corresponding eigenvalue. There is a corresponding eigenvalue. This is called non-degenerate. This is called non-degenerate time-independent perturbation theory. Time-independent perturbation theory. Now, if however, corresponding to one energy eigenvalue, we have a range of eigenvectors we call it degenerate time-independent perturbation. We call it degenerate time-independent perturbation. So here in this class, what we will do, we will subject our problem to the non-degenerate time-independent perturbation theory. Now, if I start with, what am I supposed to do is, I will choose an eigenvector, say psi n, and I can write down this eigenvector as lambda naught psi n 0 plus lambda raised 1 psi n 1 plus lambda raised 2 psi n 2 and so on and so forth. Alright? With this lambda that we have chosen here, now if I have a Hamiltonian, this Hamiltonian has an unperturbed Hamiltonian, and we add up a perturbation term to this unperturbed Hamiltonian. The beauty of this perturbation is that whatever you calculate for the perturbation term, it falls in the framework of the unperturbed Hamiltonian. So whatever you calculate for this perturbed term, you will find this perturbed term will be decorated by unperturbed Hamiltonian. Getting my point? Okay? And this lambda, if you go back to that example as I started with, a small change. You're trying to disturb your system, but the magnitude of that disturbance is extremely small. So for that, this lambda has to be small. Its value can be between 0 and 1. Clear? Okay. So this is my eigenvector, and I can write about energy. So En, I will expand it like this. En 0, lambda raised 1, En 1, lambda raised 2, En 2, and so on and so forth. So if I commit any mistake while doing some kind of algebra, you will just stop me at that time. Okay, you just tell me to rectify that. So what we are going to do here is we're going to proceed. Okay. So now I have this Hamiltonian, perturbed Hamiltonian, and I'm applying this. I'm subjecting this Hamiltonian to the eigenvector psi n, and I will have energy eigenvalues psi of n. And what we assume here, we assume here that our wave functions, our eigenvectors are normalized. Okay, they are normalized eigenfunctions. So now I can move on, and all I have to do is to use this in this, and I should rub this. So instead of this Hamiltonian, I'm going to write h naught plus lambda hp times, yeah, okay, come on, yeah, it is psi n 0 plus psi n 1. I have lambda 0 here, I have lambda raised power 1, and I have lambda raised power 2, psi n 2, and so on and so forth. I will close the brackets, am I right?
Yes, sir.
Okay, so I would like to rub this. Alright, now let's proceed. Now this is equal to what? This is equal to En. We have defined En. For En, I'm going to write lambda raised power 0 En 0 plus lambda raised, this is not that lambda, it's just a constant, okay? So lambda raised power 1 En 1 plus lambda raised power 2 En 2. I will close it, and I have to multiply it with the same eigenvector, which is a combination of all these vectors. So this is lambda raised power 0 psi n 0 plus lambda raised power 1 psi n 1 plus lambda raised power 2 psi n 2 plus so on and so forth. Now see, since we are talking about perturbation, as long as we move on the higher order terms, the magnitude is going to go extremely small. So that's why we will take this process of perturbation up to a couple of terms. Okay, so we will be discussing, we would like to discuss the first order correction in the energy, then we would like to discuss the second order correction in the energy. Is it clear?
Yes, sir.
Okay. Now, so come on, let's multiply them in such a way that we get the same kinds of coefficients. So I should rub this one now. I hope you have written it down. And so come on. So this is h naught, psi naught, okay? So this is h naught and psi naught. Am I right?
Yes, sir.
Okay, so this is lambda to the power 0. So this will be the only term. I would like to write it as lambda raised power 0. Okay? Now look for lambdas. Okay? Then try to look for lambda squares. So now let's look for the lambda. So I think this will give me lambda. Not this, I think this. Okay? So plus h naught. Yeah, come on. Psi n 1. See, this is psi n 1. Like this. Okay, another term with lambda. Lambda 1 and psi n 0.
Yes, sir.
Right? So this is plus HP. HP, yeah? Come on, tell me. Psi n 0. So I will bracket it. What's outside? Lambda. Right?
Yes.
Okay, come on, go with the third term. We'll try to go for squares now. See, h naught and psi n square. So plus h naught psi n 2. This is the first term for lambda square. And this will give you lambda square. Am I right? So this is HP. Yeah? Then psi n 1. Come on. Then close in. Then bracket it. And this is giving me what? Lambda square. Am I right?
Yes, sir.
Alright. So I think I can rub this line. Okay. Now move on. Now we have to multiply. Did I miss something? No. Now let's go with this, okay? And try to obtain the same coefficients in the right hand side, okay? So the first one will be what? This will be equal to, yeah? This will be E n naught psi n 1. So this is E n naught psi n naught. So what will be it multiplied by? Lambda naught. Am I right? Come on, look for the squares now. Plus, I think this, no, not squares, lambda. This and this will give me what? It will give me, I will not write lambda first. Okay, this is E n naught psi n 1. E n naught psi n 1. Come on. Plus, yeah, then lambda 1 E n 1 psi n naught. Then plus E n 1 psi n naught. I can close it in. Then this is lambda. Am I right? Come on. Is it observable from this side?
Yes.
Okay. Okay. So we have to go for the lambda square now. Come on. For lambda square, I think I will start from here. See, this is E n naught, and this is psi n 2. So I can write here plus E n naught psi n 2. Then, come on, this will give me with this, it will give me square. Now, so this is E n 1 psi n 1. This is plus E n 1 psi n 1 close. Okay, then I think this and this will give me the square. So plus
E n 2
yeah, this is E n 2.
psi n naught.
Okay, this is psi n naught, and I'm going to bracket it, and I'll keep lambda square outside. Alright? So I'll not go with the higher order terms, and you see, for any equation like this, you have, if this equation has to be true, then the coefficient of lambda naught must be equal from left hand side to the right hand side. The coefficients of lambda must be equal, and the coefficients of lambda square must be equal on both sides. Is it fine now?
Yes.
I think the top one I can rub. I can rub this part, and let's see where we can reach from here. So you'll write down that point yourself. Okay? So you will have the first thing. First thing, come on, what will be there? Did I rub something? Huh? Okay, we will have, yeah. No, I give you the, huh? H naught, yeah. H naught, sine n naught equals this. E n naught plus E n naught psi n naught. That's it. Okay, what is this? Come on, tell me what is this? What is this? This is unperturbed Schrodinger's wave equation. We know everything about it. We know its eigenvectors. We know its eigenvalues. Clear? Okay, give me another equation in terms of lambda. Come on. Lambda, yeah. In the left hand side it is H naught, then psi n 1 plus HP psi n naught. Don't commit any mistake here. Is he right? He's telling it right? Okay. Is equal to, yeah, come on. Okay.
E n naught
Is equal to this thing. Okay, I have it. I don't need your help here. So this is E n naught. Then you have psi n 1 plus E n 1
psi n naught.
psi n naught. Am I right? That's beautiful. Okay, so this is your another equation, and you will have the third equation. Okay, you will have the third equation. Where do I write that? Okay, I will rub this. This is, where is that lambda square term that I have obtained? Here is that. Okay, so this thing will be equal to, yeah. Come on, come on. Tell me the left-hand side of this equation. Tell me the left-hand side of this equation.
H
Oh,
naught psi n
H naught psi n2 plus HP
psi n1
psi n1
is equal to
this
En
thing.
naught
Is equal to, okay, I will write it. So this is En naught, then you have psi n2, then plus, you have En1, and you have psi n1, and you have En2, and you have psi n0. These are the three equations, right? And obviously, this is our unperturbed Hamiltonian equation. We know everything about it. And this equation will lead us to first order correction in energy and first order correction in the energy eigenvector. Okay? And this equation will lead us to second order correction to the energy eigenvalues. Is that clear? Fine? Okay. So here we will go with the first order, okay? So we would like to obtain the first order correction to this non-degenerate system, right? Where we have basically used the time-independent Schrödinger's equation. So I would like to rub these. Can I rub it? Okay, I can rub it. Okay. So this is my unperturbed Hamiltonian. Now I want first order correction. I want first order correction. I want first order correction. Come on. Now see what I'll do. What I'll do is I will choose another set of unperturbed eigenvector belonging to the same unperturbed system, right? So what I will do, I will choose an eigenvector psi m0. This eigenvector is belonging to the same unperturbed system. Are you getting me?
Yes, sir.
See, if you go to the classical world, you have the basis vectors in Cartesian coordinates. I, j, and k, right? And similarly, here you can have I1, j1, k1, and I2, j2, k2 belonging to the same basis. So what am I trying to do is I am choosing a vector psi m0 of the same basis vectors. So what I do is I multiply this equation by this eigenvector from the left side. Okay? So what I do, I multiply this equation by this eigenvector on the left side. Is it clear? So what I'll do, what I'll get here, I'll get psi m0 h naught psi n1 plus psi m naught, oh sorry, no, in this case I don't need m. I don't need m. I need m when I have to calculate the eigenvector. I will use the same basis vector but on the draw side, psi n0. Right? Okay? So I will multiply this equation both sides from left with psi n0. I'm using the same basis vector, right? Of unperturbed Hamiltonian, and I have to multiply this with this equation. What I'll get, come on, I will get psi n0, then h0, then psi n0 plus, yeah, hp, not hp, I will write psi n0, hp, and psi n0. Am I right? Okay, then is equal to psi n0 en 0 and then psi n0. No, it's 1. Hey, you are not correcting me. Come on, I want your concentration. right?
Yes, yes.
What?
First term.
First term?
LF is first term. Psi and mod.
Here. Yeah, it has to be signed. Alright? So here it is. It is the same. See your your perturbation Hamiltonian is falling in the unperturbed eigenvectors, right? So this is okay. So what will be this? It will be psi and 0. Then you will have E and 1. Then again psi and 0. Is it clear to everybody?
Yes, sir.
I think I can rub the top side now. Okay, so what is this? Come on. This is psi and 0 and psi and 1. They're orthonormal to each other, right? They're orthonormal. So what will be its value? It will be 0, right? And what will be its value? It will be 0. And what will be left with is psi and 0, psi and 0. Because I have assumed that my eigenvector is normalized, so psi and 0 will give me 1. Are you getting it? So what will I find here? Finally, I will have E and dash. Sorry, it's not dash, it is E and 1. This is first order correction to the Hamiltonian. This will be equal to what? Psi and 0 plus HP psi and 0. This is nothing but the matrix element of HP. Getting? Come on. Any questions? Any queries? Okay. So this is En dash. Now if I have to write En, what is En? En is lambda naught En naught. Okay? Plus lambda, then En 1. Plus, I will not go to the other terms, right? I will go to the first order correction to the energy. So what will I obtain from here? Okay, this is our unperturbed Hamiltonian. This is our unperturbed energy eigenvalues. And what about this? Lambda is just a number. What about this En1? En1 is what? En1 is the matrix element of what? HP. So I should write down a matrix of n by n. Okay? So what's that? That will be HP11, HP12, HP13, plus so on and so forth, so on and so forth. So here you will have HP22, and then you will have HP33, and so on and so forth. Am I right? So you will have so on and so forth from this side, and you will have so on and so forth from this side, and here you will have HP n by n. Right? So what you will obtain? Now the diagonal of this matrix will give us the energy eigenvalues of the perturbed Hamiltonian. Is it clear? Okay? So with this I would like to take some questions if you have. Any question? Come on, come on. Now after this, what we will do in the next lecture is that we will look for the correction in energy eigenvector. Okay? So that we will probably do in the next class.